Let's take a look at another example here where we are finding the area of a region bounded by a curve and the x and y axis. Okay, we're going to use the limit approach. So how do you know if I'm using limit approach or rectangle approach? Well, if you're not given a specific number of rectangles, then let's go ahead and assume that we're using the limit approach because we have to be able to eliminate n. Okay, so remember the approach in these problems is we need to either find the left hand or the right hand. It's simplest really just to find the right hand for each one of these and kind of roll with it. That's the easiest CI to find, and then we always have to find our delta x. Alright, then substitute that into the function, let the calculator do the summation for us, and then we should be good to go. So let's review one. So we want to find the area of the region bounded by the graph of f of x equals 4 minus x squared, the x-axis and the vertical lines x equals 1 and x equals 2. So I've sketched the graph out for you guys to kind of take a look at. The area of the shaded region is what we're trying to find. Okay, this is going to come in more important when we start making actual solids and things like that. You'll do most of that in Calc 2. We'll start revolving an integral around an axis and actually produce something that's 3D. So that's why it's really important that we understand how to do this setup in this case. So for us, just like the others, alright, we have to define, alright, so x equals 1, that's our A, x equals 2, that's our B on our interval. So we have to find delta x. Delta x is taking b minus a over n, so 2 minus 1 over n. Delta x is 1 over n. Remember, we're not choosing a number of rectangles, we're actually going to use the limit as n approaches infinity, so we leave it in terms of 1 over n. Let's choose the right endpoints, it's the easiest. So CI is going to equal a plus I delta x. This one's important because a starts at 1, so we need to make sure that we have that 1 in there. Alright, so it's 1 plus I times delta x. Delta x we calculated is 1 over n. So our CI, that's the value we're going to substitute into x, is 1 plus I over n. Alright, so now we go down to the area summation. So we're going to take the limit as n approaches infinity of I equals 1 to n of f of CI times delta x. We calculated CI and we calculated delta x. So our original function is 4 minus x squared. So we have to put 4 minus 1 plus I over n, that's our CI, and make sure that we square that, okay, times our width, which is 1 over n. Now, it may or may not be easier to go through this, but let's go ahead. If we FOIL out the 1 plus I over n, right, because it tells us to square it there, and we combine it with that 4, we end up with getting the limit as n approaches infinity of I equals 1 to n of 3 minus 2I over n minus I squared over n squared. I left that error out there. It should be I squared over n squared. There should be a line there. Times delta x, which is 1 over n. Alright, we're going to distribute that 1 over n through. Alright, and that's going to help us write out our different sums. Okay, notice they're all in different fractions right now, but we still need that n to kind of go with each one. You can multiply by 1 over n at the end if you want to as well. I'm going to distribute it here through. So we get the three different sums. Limit as n approaches infinity of I equals 1 to n of 3 over n minus 2I over n squared minus I squared over n cubed. Okay, now we're going to write our three different sums out. So each one of those sums, right, we have to factor an n out. So if we take this 3 over n and write it as a sum, we're going to factor it out as 1 over n times the sum of I equals 1 to n of 3. And then if we look at the next part here, alright, we have 2I over n squared. We factor out a 2 over n squared, so we have the sum of an I. And then in the last one we have to subtract, right? We're going to factor out 1 over n cubed, so we have the sum of I squared. That should look real familiar. We have something that has a constant, a sum of an I, and a sum of an I squared. That's where we go back to theorem 4.2 and we substitute in whatever the summation for I squared is, it's equivalent in terms of n. Whatever I is, it's equivalent in terms of n, and whatever 3 is, it's equivalent in terms of n. So that's what we've done here at the bottom of this page. Alright, so now our limit as n approaches infinity, everything is in terms of n right now. Now before you take the limit, do some simplification, because if you don't, you might think everything goes to 0, but it's not going to. So if we rewrite everything, so the first term is going to be 3n over n. The second term, alright, if we distribute the n through, you get n squared plus n. Alright, then we're going to distribute this negative and this 2 through. Okay, and that third term, you have to FOIL out the n plus 1 times 2n plus 1, and then multiply n through. You've done this multiple times in other examples, so you can just kind of go back and look through your notes and see what those equivalents are. The one thing you just really got to be careful of is making sure if it's a subtraction that you're distributing that negative sign to each term. So that middle term here, that negative 2, okay, that negative has to go to each term. Same with the third term over here. That negative has to distribute to each term. So really make sure that you're keeping track of where that negative distributes. Then anything that has a common denominator, we separate out as fractions, individual fractions. So when we do that, I'm down here on the third line here with the limit here. We're going to take the limit as n approaches infinity of 3 minus n squared over n squared minus n over n squared minus 2n cubed over 6n cubed minus 3n squared divided by 6n cubed minus n over 6n cubed. Alright, let's reduce some more of the n's down so we can actually get to values we want. Once we do this, it's really easy to take the limit. Okay, so we're going to have 3, this n squared over n squared becomes 1, that's pretty obvious. N over n squared becomes 1 over n. We have n cubed over n cubed, those eliminate, become 1, and this 2 6 becomes a third, so we have minus a third. Alright, and then we have 3 over 6 reduces to 1/2, and since we have n squared over n cubed, we have an n in the denominator, and then the last term, 1 over 6n squared. Now remember taking the limit. Anytime we take the limit as n approaches infinity of 1 over n, or 1 over n squared, or 1 over n cubed, or 1 over n to the 10th, whatever, anytime it's 1 over n something, that part goes to 0. So don't cancel out your constants, alright? The 3 minus 1 stays. But as we approach, or as we take the limit, as n approaches infinity of 1 over n, that piece goes to 0. The 1/3 is a constant, it stays. As we take the limit as 1 over 2 times infinity, that's 1 over infinity, that one's going to go to 0. And then we have 1 over 6 times infinity squared, that's also going to go to 0 as we take the limit. So those 3 n terms are going to drop out. So we're left with 3 minus 1 minus a third, which ends up being 5/3. So that's the area of the shaded region under the curve here. So if we scroll back up, that's the area of this shaded region. It ends up being 5/3. So there's doing a limit problem where the intervals don't start at 0, they go between 1 and 2. Alright, so if we just kind of review what's going on. Alright, this is just the limit process. Review. Basic steps for us, always find delta x first. Alright, well I guess if we back up a little bit, alright, identify what a and b are, and from there we have to find delta x. Then, once we know a and delta x, we find our CI. That's the intervals. Okay. Then, once we know delta x and CI, we substitute them into the area. Alright. And then we're going to take the limit. Okay. That area on step 3 should have a limit there as n approaches infinity. It is missing from that step 3, so make sure that you incorporate that into your notes as we review. The area should equal the limit as n approaches infinity of I equals 1 to n of f of ci delta x. So please make sure that you add that in. And then once we've done that, right, we replace all the sums, we factor out all the n terms, and we replace all the sums of I or I squared or I cubed or just a constant with their theorem 4.2. Okay, the next example we're going to go through, I'll do it in the next video. We're going to take it one where we actually have boundaries on the y-axis instead of the x-axis. This might be a question that you might see show up on a test. or something like that. So everything else we've been restricting things, and done everything with respect to the x-axis. Now we want to do everything with respect to the y-axis. So when we say with respect to the x-axis, that's where our intervals are. We went from 1 to 2 on the x-axis, okay? And then we're bringing everything down to the x-axis here. It's going to look a little different in the next video, but we'll pick that up. Hopefully this one helped out for you.